As you can see, the top hat is 7423, very exciting. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you'd guide our steps today, help us to understand a little bit more about your creation, about college algebra, and help us to just help these students to be encouraged if they're struggling, just to do their best, Lord, each day for your glory. In your name I pray, Lord Jesus. Amen. So there's the top hat. So let me start with an example here. So we're talking about logs and exponentials today. And we're going to talk about their properties, what they are, what their graph looks like, how to solve equations involving them, all this kind of stuff. All right? So I thought I'd warm up for you guys today with just a graph. So example 1, graph y equals to, let's say, 2 plus 3 to the x minus 4. And let's call this thing f of x, all right? Find the domain and range of f. All right? So I'm going to use the idea, the transformation of graphs idea, to construct the graph. Okay, so here's how that's going to go. We talked about last time a little bit, just briefly, but basically this is the deal. 3 to the x looks like this. All right, it's got a y-intercept of 1. If you go 1 over, you're at 1 comma 3, right? If you go 1 to the left over here, you're at like 1 minus 1 comma 1/3. Okay, so this is what the graph y equals 3 to the x looks like. If we look at the formula we have, what are we going to do? We're going to do what? We shift right 4 and up 2. Yeah? So we want to shift right 4 and up 2. All right? So, the couple different big features of the exponential function. One big feature is it's got a horizontal asymptote of the x-axis, right? So like, what's going to happen if you shift the asymptote right to the 4, nothing happens, right? It just stays put. But if you shift it up 2, that gives you a new horizontal asymptote of 2. So I've got like a horizontal asymptote at 2 for the new function, right? And we can kind of just track the other points to get the graph, right? Like the point minus 1, 1/3, it shifts right 4. So on the new graph, I'm going to have the point add 4 to the x, I get 3 1/3. So, so something like here, that point, 3 1/3. Well, not 3 1/3, is it either? Where is that? It's not 1/3, it's now where? 2 plus 1/3, right? That's one point on the graph right there. And the y-intercept of the original graph transforms to, you move over 4 and up 2, right? So you go so this was the point 0, 1, right? 0, 1 is going to map to, I go to 4, where? 4, not 2, but 3, right? Because we go over 4 and up 2. And then this point, 1, 3, I go over 4, which is, 1, 3 goes, what? It goes to 5, and 5, 5 actually, right? So something like this, yeah? Okay, and now we can graph the transform function, right? What's the graph look like? It looks something kind of sort of like that, right? So there you go. There's my best on the fly on the board I can do for you. 2 plus 3 to the x minus 4. That's what the graph of this looks like. Now, so there you go. There's the graph of f of x. So now you guys tell me, what's the range, what's the domain? What's the range? I'll do the easy part. The domain is everything. It goes on and on both directions. So the domain is just everything. What's the range? So can anybody tell me what the range is here? 2 to infinity. Now is 2 included? Not included, right. So 2 to infinity. So there we go. So that, folks, is a graph of, now I would say, so and here's where the language gets a little bit dodgy. Some people might call this an exponential function. I would say, technically speaking, that's not quite accurate. It's not an exponential function. It's a shifted exponential function, all right? Because the exponential function, when I talk about exponential function directly, I'm talking about this. This is an exponential function, all right? This is a shifted exponential function, but you have some of those in your homework to graph, so I thought I should go through one. So I told you guys I'd get a graph out here. So let me do that for a minute. Let me shift my camera over here. So I just wanted to talk about the shape of the graph of the exponential just a minute or two here. Oops. So here it is. What am I looking at right now? I'm looking at, I selected the 2 to the x. This is what 2 to the x looks like, okay? And so, great. What does 3 to the x look like? Well, 3 to the x, I'll click this button right here. It looks like that. So the 3 to the x is blue. Does this make sense? So if you take 2 and raise it to a positive power, it's smaller than 3 raised to the same positive power, right? That makes sense. 3 to the x is over 2 to the x. And then the story reverses down here, see? Because if x is negative, what's 2 to a negative power? That's like 1 over 2 to that power, right? So like, for example, 2 to the minus 1 is actually 1/2. And so if you look at minus 1 here, the 2 function is at, well, here's minus 1. So, oh man, I was just trying to, come on, let me go down, there we go. Okay, so right here, at minus 1, 2 to the x is at 1/2, right? Whereas 3 to the x is at 1/3, okay? And of course, by the time you get to minus 2, 2 to the x is at 1/4, and 3 to the x is at 1/9. All right? And so that's how that works. So here's the interesting thing. If you look at this, if you think about this, we can kind of, you guys know what a slope is? We know what the slope of a line is, right? So if you go on to study calculus, you'll talk about something called a tangent line, right? A tangent line is a line which it resembles the graph close to a point. It's like the best linear approximation to the graph at the point. If we look at the origin, I mean the y-intercept here, right? You can kind of see that there's a tangent line like this here for the blue graph, right? Which is what, 3 to the x? And if you study that, you can pretty easily see that the blue graph has a slope which is like bigger than 1. If you look at that, you can see that the slope of the tangent line to the blue graph is bigger than 1 because it goes over less than 1, but it goes up more than 1. I mean, it goes up 1 and less than 1 over, right? On the other hand, if we look at the green graph here, right, the slope of that line is what? It's going over 1, it's going up less than 1. So the slope of the green line at the origin, I mean at the y-intercept here, is smaller than 1. So blue line, slope bigger than 1, green line, slope less than 1. So if you think about that, you know, you can look at slope, all different possible slopes, right? Here's in red. This is what all the different slopes look like. See, here I'm looking at a varying between 0 and 4. So here's all the exponential functions between 0 and 4. I'm just different a is being animated, right? So of course, when you get to, so let me just talk about this a little bit slower here. Like if we go to a equals to 1, it's really boring. Check this out. So like a equals to 1, 1 to the x is just the constant function 1, right? But if you do base a larger than 1, what happens is you start to bend up, right? So by the time you get to, there's like 1.48. See how it's getting taller and taller? You get over here to 3.2. It's a little bit above my 3 to the x, right? And so it just keeps, but you see that there's this continuous family of exponential functions that are steeper and steeper and shallower, right? You can adjust the value of a to get all these different curves. So if you think about this, right, there should be between the blue line and the green line, there should be some exponential in there that you have slope 1 at the y-intercept, right? Let's see if we can find it, slope 1. So maybe about like right here-ish. If you look at the red one, if you can see it, it's, well, I can't quite see it, but I guess it's got to be a little bit bigger. I'm not sure. I think my scale is, I jumped, well, maybe that. If I could just focus in here on this little square, right, you can see that the red line kind of goes over 1 and up 1. Basically, the slope of the red line, if I just zoom in there, it's slope 1. Okay, there's some exponential, there's some base in this story which has slope 1. That's the special base, which is called e. So y equals e to the x, I've got in black down here. It's the slope, it's the exponential function that is between 2 to the x and 3 to the x, which when you go through the origin, it has slope 1. This is a very special case. It's called base e. And so definition, so we have f of x equals a to the x is an exponential function. For a greater than 0 and a not equal to 1. All right, I'm going to put this away because we don't need any more. I hope you top had it already. It was 7423, so. Okay, so it's an exponential function. We do need a not equal to 1 because 1 is too boring. It's just that constant function. So we wouldn't call that an exponential function, but we could have a positive less than or greater than 1, like that. Then, so the case a equals to e gives f of x equals to e to the x. This is the exponential function. So I say the exponential function because it's a special one, okay? As to distinguish it from, there are many, many choices of a. 2 to the x, 3 to the x, 4 to the x, 5 to the x, 10 to the x, whatever to the x. Exponential functions, right? E to the x, this is a specific number. That e, turns out, is about 2.71 da 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 da. All right, this is Euler's number, in honor of Euler, who was a well-known mathematician of the 18th century. Pretty much everything we do in college algebra, he was one of the first people to really do it clearly in a way that was communicated to a large audience. All right, and we're still doing things with more or less his notation for the most part. But anyway, that's the exponential function. Now, in your calculator, right? In your calculator, you actually have this e, right? If you look at, like, my calculator has e to the whatever, so I can go like, e to the 6th, and it'll tell me, for example, e to the 6 is equal to about 403.43. There you go. So you can calculate e to whatever in your calculator typically, all right? And of course you can also calculate a number to a power as well. So that's the exponential function base a versus exponential function base e. So just to reiterate here, here's the basic story. If we look at graphs, we have basically two cases. We either have, right, a graph that more or less looks like this. This would be something like y equals a to the x, where a is greater than 1. Okay? And the other possibility is we can have an exponential function that is sort of the mirror of this, the other way, like that, all right? And this would be something like y equals 1 over, well, let's say it this way. We could say a to the x, but here 0 is less than a is less than 1. So if the base is between 0 and 1, it looks like that. Now, notice that, for example, y equals 1/2 to the x, we could also write as what? Two to the negative 1 to the x, right? And by one of the laws of exponents, which you may or may not have forgotten, this is 2 to the minus x. And so, look, there's a natural way to understand the fractional bases just in terms of, oh, so you're replacing x with minus x, right? So of course the graph is the reflection across the y-axis, yeah? So that's why the fractional ones look like this, because they're just basically changing x to minus x in the other formula. Okay, so like if 0 is less than a is less than 1, that makes 1 over a greater than 1. So, well, let me. Hey, you know what? I don't think I'm gonna. I think I'm gonna lose a lot of you if I chase that rabbit. And let me just let it be. Okay, so this is the exponential function. What up next? We can talk about logarithms. All right. So f inverse of a to the x is equal to log base a of x. Okay, and so in the special case, so this is where f of x is equal to a to the x. So the inverse function to a to the x is log base a of x. All right? And in the particular case, when we have f of x equals to e to the x, then log base e of x is a special notation. It's called ln of x. ln of x is what's known as the natural log. I can't spell today. What's wrong with me? Golly, natural log. Somehow the spelling of natural has become unnatural to me. I don't know what's wrong with me, but that's the natural log. All right. So what are the properties of the logarithm? So before I do properties of the logarithm, let me remind you properties of the exponential, okay? So like here's how the exponential works. If we have a to the x times a to the y, what do we get? If we have a to the x over a to the y, what do we get? If we have a to the x to the p power, what do we get? Right? What's a to the 0 also? What's a to the 1? What's a to the minus 1? Let's talk about these. Now, if you don't know them yet, now's a good time to learn, because these are things we all need to have memorized and know without like looking in a book. Like we should just know these things for future reference. Okay? But if you don't know them yet, if you're not confident about them, that's okay. That's why we're here to learn, right? This thing keeps trying to recoil on me. There we go. All right. Okay, so number one, we've got a to the x plus y, all right? Number two, we've got a to the x minus y. Number three, we've got a to the x times p. Number four, a to the 0 is 1. Number five, a to the 1 is a. A to the minus 1 is 1 over a, okay? These things are all true. Now, what else is true is that there's corresponding laws for logarithms. All right, let me write for you the corresponding rules for logarithms to the right here. I'll make another column. So like log base a of x times y is equal to log base a of x plus log base a of y. So that's one of the properties of the logarithm, is that the log of a product is the sum of the logs, which is actually kind of a big deal, because that means we can trade multiplication for addition with logarithms. That is an incredible simplification, really. Also here, the corresponding property for logs, we have log of a quotient, like log of x over y is log base a of x minus log base a of y, all right? The power identity for log is like this. Log base a of x to the power p is p times log base a of x, all right? And then here's some basic ones, right? So like log base a of 1 is 0. Log base a of a is 1. Log base a of a to the minus 1 equals minus 1. But the more fundamental thing about all of these is we should remember, by definition, we have that a to the log base a of y is equal to y, and we have that log base a of a to the x is equal to x. The identity on the top is true for y positive, y an element of 0 to infinity, and the last one is for x, any real x, from minus infinity to infinity will do. Okay, so this is how it works, all right? These are the main tools we have to work with. Now there's a couple sneakier things I can share with you, and I probably should. Let me just get them out of the way here. I'll present them right now, just to. So we'll need them at some point, all right? So let's just get it out in the open. And I really should prove these laws for you at some point, right? But not today. Okay, we're going to work problems with these rather than proving them, if that's okay with you guys. But the other thing is kind of sneaky change of base ideas. So here's one thing you can do. Check this out. This is very sneaky. So we can take ourselves from a to the x, right? And watch this. This is very, very sneaky. I can trade x for e to the natural log of x. Oh man, that's not what I wanted. The other way around. My bad. Natural log of e to the x is what I wanted. There we go. See, because x is equal to. One thing I should mention. I wrote all of these identities for a in log base a. They're also true for the natural log, right? How would you reiterate? How would you reproduce this column, this bunch of truths for the exponential, for for a equals to e, you just basically take your log base a and swap it out for natural log, and you take your a and swap it out to e. In all of these identities, they're still true. Just rewrite with natural log and with e instead of a. They're still all identities, okay? So like this here, this is because, you know, the natural log of e to the x is just equal to x again, okay? So see, I've just rewritten x as e to the natural log of e to the x. But what else can you do? What else can you do there? See, we can apply the this property right here. We can pull the power out, right? I can pull x out of this, like this. This is equal to a to the x. Oh man. Well, that just took me in a vicious circle. I'm remembering this wrong, guys. Look at this. This is true, right? I mean, I'm using property right here with x equals to e and p equals to x. So like this looks like, well, anyway, since I have e to the something, I can pull the power out. And what's the natural log of e? That's like this, right? Log base e of e is equal to 1 means the natural log of e is equal to 1. So what have we got? A to the x equals to a to the x. I wouldn't say that that's sneaky. I would say that that's just like a waste of your time. I'm sorry about that. I mean, it's not a waste because I'm showing you identities which are true, and hopefully you're learning things from this, but that's not what I wanted to do. Let me derive it, if you don't mind. So my claim is that we can write a to the x as equal to e to the y for some choice of y. What would you put for y? Can you solve for y? So what I would do if I want to figure out what y is, what I want to do is I'm going to take the natural log of both sides of the equation. All right, so I take natural log of a to the x equals to natural log of e to the y. But natural log of e to the y is just y again, okay? Because the natural log and the exponential are inverse functions, so they just cancel each other out. And on the flip side of things, we've got, you know, y equals to, therefore, y equals the natural log of a to the x. How could you guys simplify natural log of a to the x? Do you guys know? We can use this property here. So let me rewrite this property in the natural log notation so you guys can see it more readily. This says that the natural log, and I'm not going to use x, I'll use something else. Natural log of big A to the big B power, let's say, is b times the natural log of a, okay? It might be a good idea for you to write the logarithm properties in different letters than x and y. Like, it's a good exercise. Go through, write these properties. Instead of using x and y, maybe use a big A and big B so you can see the pattern, right? Because maybe you'll be working problems where you have x and y, and you know, if you have a problem that has x and y, and you've got these identities written in x and y, it's harder to see how to substitute them, right? If you have the identities written in a and b, then you can think about setting a equals to x, right? Well, anyway. Okay, so that, basically I'm just saying the x is a power here, right? So it pulls out. This is x log a. So what this shows us is the sneaky theorem. So fun fact, basically. We can rewrite a to the x as e to the y, right? But I'm going to get straight to the point. It's e to the x times the natural log of a. What does that say about the graph of a to the x versus the exponential? Do you remember how it works? If you take one formula and you multiply the argument by a number, that's a horizontal stretching or compressing of the number, right? Like if the natural log is, if the number here is larger than 1, you're compressing the graph. If this number is less than 1, you're stretching it out. But anyway, this is just a neat, so any, you know, if I have, so application here, I guess this is example 2. I can rewrite, for example, 3 to the x is equal to e to the x times the natural log of 3. There are places where this is like very helpful. Okay, because the other thing is, there's also a change of base formula for logarithms. And this is actually more useful in some sense. If we have log base a of x, we can rewrite that as the natural log of x divided by the natural log of a. So this is the so-called change of base formula. You can also, this is, I mean, I've written it for base e, but more generally you can write it like this, like log base b of x divided by log base b of a. So this is the so-called change of base formula. Definitely something you want to have on your formula sheet for next test. Why does this matter? Well, suppose you want to calculate like log base 7 of 13. How would you do it? Look at your calculator. Do you have log base 7? Is there a log base 7 on your calculator?
I don't have it with me.
You don't have it with you? Don't have it with you? Ah. I'm just joking. I mean, it's okay. I will tell you, most calculators don't have log base 7. Most calculators don't have log base 3. Most calculators, at most, you're going to find log base 10, log base e, and if you're lucky, log base 2, which is sometimes called LG. So log base 10 is sometimes called the common log because it's based on powers of 10, you know. And but this one here, we can switch to this. So this is we're going to do natural log of 13 divided by the natural log of 7. And if you've got a scientific calculator, you've got a natural log button on it. Okay. So I just go over to my handy dandy calculator and I calculate, you know, natural log of 13. And I divide by the natural log of 7. And when I do that, out pops, oh man, 1.318 approximately, okay? So I can use the change of base formula to straight calculate values of non-standard bases, okay? So like on this calculator, oh, actually, I spoke too soon. This one actually does have log base 7, but it's, I gotta like hit the log button. I don't know, I gotta like, I'm not sure yet. Maybe you have to press like the shift log button. Nope, that's not it. I don't know. I gotta press some special buttons to make the log button work. You found it? Did you have log base 7?
I just did I have the TI-80 plus calculator.
Ah, see, that one is not. That one would not be allowed on the test, unfortunately, as it is a graphing calculator. But you might have a log base 7 on that. It seems likely. Let me steal it from you.
It's number 5 on that menu.
Oh, cool. There you go. Now, of course, you know, guys, I mean, in the age of the internet, can you calculate log base 7 of 13? Sure. Just go to like any of your favorite math websites, like I like Wolfram Alpha. Put it in there, and it's going to tell it to you, right? But there was a time when this was not possible. How would you calculate, you know, logarithms of big numbers? So let's see here. Let me do another example for you. So the general itch I'm scratching at the moment is how do you actually calculate numerical values for logarithms? Okay? So sometimes you can just use the definition of the logarithm and you can calculate it pretty easily. Right? For example, what am I on here? Example 4? Thank you. So in typical American books, just plain log means log base 10. However, beware, there are scientific books which use unadorned log to mean the natural log. All right, so there is some disagreement about this notation, but let's say it's log base 10, okay? And if I wanted to calculate log base 10 of, oh, I don't know, let's say, 10 to the 17th, how would you do it? What is log base 10 of 10 to the 17th? What's that? It should just be 17, right? This is just equal to 17. Yep. What if you were to calculate, log of, oh, I don't know, 300 times, 2 million. See, you could rewrite this, right, as log of what? 3 times 2 times what? This is what? This is 3 times what? 10 to the 2, right? This has got a 10 to the 2. It's 100. This has got a 10 to the 6th, right? So when you multiply those, you get 10 to the 8th. And so this would be equal to what? This would be equal to log of 3 plus log of 2 plus log of 10 to the 8th. What is log of 10 to the 8th? That one's easy, right? Remember, log is log base 10. So it's the common, this is aka the common log. So there's common log, there is natural log. I gravitate towards natural log because like it appears in science a lot and I like science. Real science, not the kind you believe in, So this here is 8. Yeah? What is log of 3 and log of 2? So I get my calculator out, right? And I go log of 3 is 0.4771. I'll keep 5. Log of 2, I get 0.30103. And so then you add these. And I get 8.7781, approximately. Right? But what if you wanted to give an exact answer? If you wanted to give an exact answer, one way you could give an exact answer would just be to say that this is, technically it's equal to, log of 3 plus log of 2 plus 8. This would be an exact answer. So sometimes we're interested in you understanding that this is equal to that, that kind of thing. I would lean towards like a multiple choice format on this kind of question, which of these numbers are equal kind of thing we could do. But now, of course, you can always fall back and calculate them on the calculator and compare their decimal forms, right? It's easy to tell whether two numbers are equal if you just look at their decimal forms, right? Telling whether two numbers are equal when they're expressed as a sum or a logarithm It can be complicated. They can look really different even when they're the same number. Now, so I stole a prop from Dr. Putney. So he has 2 of these. He let me borrow it. So like this, do you guys know what this is? Well, I guess it's kind of right there, right? So this is a slide rule. So once upon a time, you guys didn't have calculators because, you know, before transistors, there are these things called vacuum tubes, and like to bring a calculator to class would have been something like at least the size of a refrigerator, if not a room worth of electronics, right? The first computers filled rooms this size, you know. But this here it's a mechanical thing that by sliding this back and forth and looking at how things line up, it allows you to calculate the values of logs of numbers. So if you understand the values of the logs of numbers because you've got your log rule, which is basically a complicated way of having a giant table of logarithms, you can use that paired with the properties of logarithms to calculate, do arithmetic with numbers like this. So it's, you know, not my generation, but the generation before mine still used slide rules. Dr. Putney said they were used in universities up until the mid-'80s, which is when calculators became widely accessible and cheap. I mean, people did have calculators back in the 70s, but I mean, electronic ones, but it was kind of more of a novelty at that point. And of course, nowadays, you know, who doesn't have a calculator, right? And so Dr. Putney also pointed out that if you want to learn how to use these, you can look it up on the internet. There's good videos. But the idea of looking at a video on the internet to learn how to use a slide rule does seem a little bit backwards, doesn't it? So, Dr. Dromby, I was talking. Excuse me, not Doctor. Professor Dromby I was talking to her, and she actually had a student, I think last semester, take a quiz using a slide rule. It's like something on his bucket list for reasons I don't understand. Oh man, have I been focused over there? Oh, I am the worst cameraman. But you guys are all here, right? So there's that. Let's solve some problems now. Sorry, it takes me a while to get all of these facts out for you. Probably I should have just said, read the book, you know, but oh well. I'm going to erase these. Let's solve some problems. Let's solve example 5. Something like, see here, 5/3 to the x power equals 27 over 125. Now this one is kind of easy in some sense because we could do this without calculators. Like this one's simple enough that because of the numbers involved, we can just like kind of work our way through it without a calculator. Let me do it. All right, so all right, what is 27? What's 125? See, this is 3 to the 3rd power, right? And that is 5 to the 3rd power also, yeah? So what you're looking at is 3/5 to the 3rd power. Now, can you guys tell me how to make that look? How can I change that to a 5/3? Right, I can say that this is really 5/3 to the -1 power to the -1 power, all to the 3rd power. I don't know, however you want to think about that. In other words, what I'm saying is that this is actually equal to 3/5 See, because the inside one here, right, is 3/5. The reciprocal of 5/3 is 3/5. But then that's raised to the -1 power, and then I'm cubing that, right? And then by the law of exponents, I multiply the exponents. So I've got 3/5 to the -3 power. Now there are various ways to solve this equation. One way you could do it is with the one-to-one property of the exponential. Do you know what the one-to-one property of the exponential is? So check it out. So if we have a to the x1 equals to a to the x2, it implies that x1 equals to x2. This is the one-to-one property of, a to the x. The reason that's true is because the graph of the exponential satisfies the horizontal line test, That's definitely true. And so recognize that we can apply this here because I've taken the time, I've made the effort to rewrite 27/25 in terms of, oh man. This is why we can't have nice things. My bad, I should have, that was still 3/5. If you guys are confused, there's a good reason for that, because I typo, Why can I raise 3/5 to the -1 to the -1? Because that's just raising it to the 1 power, right? Listen, if you don't like this step and you prefer this one, that's fine, right? Maybe you guys are lost on this step, but you can understand directly, right? Can you understand directly if we go from here to here? Does this make sense to you? It shouldn't yet, because I did what? Man, I'm sorry, guys. I've been making dumb mistakes today. So, you got it? So, we take 3/5 is the reciprocal of 5/3, right? Then -1 times 3 is -3, so I have 5/3 to the -3 power. So, altogether, we have 5/3 to the x is equal to 5/3 to the -3. What does this tell me? X equals to what? What's that?
X equals
-3, right. Phew, man, I really picked a lemon there. Let's work another one here. There's another way to work that problem. Example 6. Maybe I'll do that next time. 2 to the 2x minus 3 equal to 16. I should have done this one first. My bad, guys. This one's so much easier than the last one. See, so 16 is what? 2 to the what? This is 2 to the 4th power. So then by the one-to-one property, 2x minus 3 equals to 4, which means 2x is equal to 7, which means x is equal to 7 over 2. I understand why these problems are in your homework, and I understand why we cover them, but I think there's also something fundamentally artificial about them. Do you guys have a good number sense? Is it so obvious to you that 16 is 2 to the 4th? I think most people, if you just walk down the street and go, 16 is what? Most people aren't going to be like, oh, it's 2 to the 4th, right? You guys know it's 2 to the 4th because you're in college algebra right now and you've been playing with numbers all semester, right? Outside of that context, 16 is just whatever number. There is another way to do these we'll talk about next time, which removes the need for the number sense. We have a sort of just an operational way of doing it, which I'll show you next time. So there is a simpler way to do both of these examples, which doesn't require sneakiness, let's say. So.